something, right? It's positive that way. It doesn't really matter exactly what it looks like yet because we're really only sketching it. We know that on this interval, which is between here and here, it's negative. And then also from here to here it's negative. But there's a 0 right here. So what that means is this is going to look like some kind of negative curve, but it has to come back up in order to cross this axis. However, since the next interval is also negative, it doesn't actually cross the x-axis because then that would make it positive. Instead, it sort of hits it and bounces back off. And then this whole interval has to be negative as well, but at 1 it's 0 again, so we know that this one also kind of curves back up and hits there. Then on the final interval it's positive, and so I know that it looks something like that. If we actually go to the real graph of this function, I'm going to not try to draw it, but instead just show you. So that is the actual graph of that function, and we can see that while it has all the key features that my graph does, my graph does not happen to look very much like it, and that's just because I didn't use any test points to figure out exactly how negative that interval goes, and it turns out it does go fairly negative. Yeah. So the important part about this is to notice that I'm actually going to clean up this drawing just a little bit to give us something to look at. And so I know that this goes like here and touches it at one point and then like that. And the crucial thing here is we have 1, 2, 3, but because it's being squared, there's actually 4 terms here, because this is the same as 3x plus 1 times 3x plus 1. So if every single one of these terms contributes a 0 to our graph, how come we only have 3 points where it's 0? And the answer is that we actually do have 4. It's just this point, where it only touches it and doesn't cross, counts as 2 zeros. And this is something we're going to talk about later in this section, which is called a multiplicity. So in this case, we have a 0 of multiplicity 2 because there are 2 zeros coinciding. Again, there's going to be more on that later. Another question we can ask about the functions in general, but I guess right now specifically polynomials, is what does it do over really, really, really large numbers or very, very small numbers? So basically, what happens as the x value goes to negative infinity or goes to positive infinity? And this is sort of asking what is the grand scale or the zoomed out behavior of this function? Well, we can do some examples to see that, well, the sort of punchline is going to be that it really only depends on what the leading term does. But for example, let's do 2x cubed plus 16x squared plus 4x minus 6. So, first of all, what's the degree of this polynomial? It's going to be whatever the highest x exponent is, and in this case it's 3, so this has degree 3. So we know that it roughly looks like x cubed. It has other things which sort of mess around with it, but we know that it has at least the shape of x cubed with augmentations. And then we can say, what happens as x goes to infinity? Well, as x gets really, really big, this negative 6 becomes very insignificant to how it actually affects the shape of the graph. Basically, if we're talking about the difference between 200 trillion and 200 trillion and 6, that's a very small difference. So this term becomes less and less important as x gets very large. Likewise, we can say that this term, the 4x term, also becomes insignificant because for a very, very large x value, we are here cubing it, which makes it really big, squaring it, which makes it bigger, and then doing nothing to it, so it's still big, but it's not even close to as big as these two. So, again, it's like the difference between 200 trillion and 200 trillion and 1,000. Even though 1,000 is a fairly big number, it's nothing compared to these other numbers. So, as x gets closer and closer to infinity, this term becomes insignificant, this term becomes insignificant, and in fact, if we keep going bigger and bigger, we will reach a point where even this term becomes insignificant. What this does for us is it says that as x gets larger and larger, the function sort of can be approximated by just the first term. And in fact, in the notes, I managed to show this, where when we look at this graph sort of zoomed in, it looks like, something really, really complicated. And then I also put the graph of just 2x cubed, which looks like that. Zoomed in near the origin, they don't look very similar at all. However, that's because we are using small x values. If we zoom out really, really far and play with the axes a little bit, just so that we can see it better, then we get something which looks like this is going to be like 6 times 10 to the 15, and, negative 6 times 10 to the 15, and very, very large numbers. So we're zoomed out very, very far. But we find that our function, the actual function zoomed out at this level, looks almost identical to the graph of just 2x cubed, which kind of corroborates what the logic says, that at very, very large numbers, or likewise at very, very small numbers, meaning towards negative infinity, the effect that this term has on the output dwarfs the effects that everything else has. And that's just because it has the highest power, and so it grows the fastest, or shrinks the fastest, or whatever it happens to be doing. So, at very, very large or small x values, we can sort of roughly approximate our function by just the leading term. So here's another example of where knowing the degree of a function becomes helpful, because if we knew that, or if we noticed that this has degree 3, then we could say, all right, so everything less than 3 becomes insignificant. And then we could use this approximation to say, at least over very, very large scales, the two functions, 2x cubed and this whole thing, are practically the same, or at least they are indistinguishable at large numbers. So while that doesn't help you at the small scale, it does tell you sort of what it does after all the big numbers and before all the small numbers. And we call that thing that's sort of taking place at the end of everything else, the end behavior, because mathematicians are very clever. And so yes, we can look at, in general, if we had not a specific polynomial, but again our generalized polynomial, right? If we have something of degree n, then we can basically say that as x gets very, very large, I guess I should say as x approaches positive or negative infinity, because it also applies going the other direction, then the function is roughly the same as just the first term. And this is again for exactly the same reason. We know that x to the n is going to grow or shrink faster than x to the n minus 1 and faster than everything else. And so the effects that this term contributes for very large x values dwarf the effects of everything else. And so at very, very large values, or when you zoom out really far, these two look the same. This helps us because we can say, all right, if I have something like f of x equals 10,000 x to the 12 minus 42 million x to the 5th plus whatever, right? I'm not even going to continue because they become insignificant. And I say, what does f of x do as x goes to positive infinity? And so while without what we've just been talking about, that would be kind of a daunting question, we can now say that, well, the highest term, presumably, like I can actually just finish this. The highest term is going to be the x squared, the x to the 12th term, and so this thing is going to dwarf everything else. So even though we have an x to the 5th, which is in its own right a fairly large exponent, and it has a ridiculously large coefficient, when we zoom out far enough, which far enough infinity is definitely going to encompass, none of that matters, and the only thing that matters is what 10,000 x to the 12 does. And, well, I don't know exactly what that does, but I know that this is an even exponent, and so it's going to take a number, a positive number, and make it something bigger, but still positive. And also, it's going to take a negative number and make it bigger, but positive. So, I don't know exactly what this function looks like, but if I zoom out really far, I know that it's going to look roughly like that, where there's some kind of nonsense going on here towards the origin for smaller numbers, but grand scale behavior, as x gets closer and closer to infinity or becomes bigger and bigger, this goes up. So the answer would be f of x goes to positive infinity as well. And we can tell that basically at a glance because this function, while it has multiple terms, we only need to look at the term with the highest exponent to figure out the long-term behavior, and I see that it has a positive exponent, so I know that it's going to go to positive infinity. If instead I had a negative here, then everything else applies. It's just now because the coefficient is negative, it is going to change the orientation of this. And so it's going to be the exact same thing, but curving downward. And so if it were this, then we would say as x goes to positive infinity, f of x goes to negative infinity. And so the coefficient does matter, but really only if it's positive or negative, not necessarily the exact value. So that's end behavior. Another thing that we have been using for quite a while, but haven't actually formalized, is something called the intermediate value theorem. And this one says that if f of a is less than f of b, and k is between them, we know there exists some x equals c value so that f of c equals k. And so this is sort of the formal way to give it, just as I gave the formal definition of one-to-one in the last lecture. This is the formal way to describe the intermediate value theorem. For our purposes, what this really comes down to is saying if I use test points on a graph and I find that at x equals 2, the graph is negative, and at x equals 3, the graph is positive, well, I have negative, positive. I know 0 has to be in between them, right? 0 is in between every positive and negative number. So I know that if it was negative at 2 and positive at 3, for some number between 2 and 3, the function is going to equal 0. And so I can sort of home in on the zeros of a function by using the intermediate value theorem. This is actually used all the time, not just in like calculus, but also in very advanced levels of math where you're trying to approximate something or solve for a very specific value. and use the intermediate value theorem to just sort of always use test points to home in closer and closer on the value you are specifically looking for. And that's just because for a continuous function, which all polynomials are continuous, for a continuous function, if it's negative down here and positive up here and continuous, there has to be a way to connect between them. There is no way to connect between them where it doesn't cross the x-axis. So there's always going to be a 0 between any 2 points that have opposite sign. This is useful for us because we used this when looking for like solving. I'm going to erase this. We did this every time we said solve absolute value of x minus 1 is less than or equal to 2, right? So we're solving for the solution space of this, which happens by breaking open the absolute value, adding 1 to both sides, and then we say, okay, so here we found our solution, but we could also represent this on a number line and say, if we want to say where this thing is positive, let's say, then, so one way to have solved this is to do the same thing, so negative 2 less than or equal to x minus 1 less than or equal to 2. Now if we subtract 2 from everything, then we get negative 4 less than or equal to x minus 3 less than or equal to 0. And so now we have things set up in terms of solving for a 0. Then we can solve for the 0. I'm not going to, but let's just say that it happens to be right there. Then we've split our number line up into 2 intervals, and we know that because this is 0, let's say f of x equals 0.